Hello everyone, and welcome back to some more remote learning. In today's video, we're going to go over limits at infinity. Now, limits at infinity, as x approaches infinity, we're either going to have our function approach some finite value, or our function is going to approach some infinite value. So, as opposed to taking the limit of f of x as x approaches some finite value a, we're now going to go through a few examples of taking the limit as x approaches some arbitrarily large positive or negative number, so as x approaches infinity or negative infinity. So let's take a look when the functions also approach infinity or negative infinity as x approaches infinity or negative infinity. So zooming on in here, you can see that as x approaches a positive infinity, that means x continues on towards the right for our graph. The limit as x approaches a positive infinity of our function, I'll call this function f of x, what's that going to equal? Well, if we follow along with f of x, where is it heading towards? It's going to continue to get larger and larger. So as x approaches some infinity, f of x also approaches infinity. Whereas here, if we look at this other side, as x approaches negative infinity, so moving to the left on our graph, our function approaches what? Same as the right-hand side, our function is going to approach some positive infinity. So here, the limit as x approaches negative infinity of our function f of x also approaches infinity. When we have some even function, they're both going to approach infinity, or if this function was flipped, they would both approach negative infinity. And this is very useful when thinking about degrees of polynomials, which we'll get into later in this worksheet. And just like I said, envision if this function was flipped. So now we have a parabola that opens down. Well, let's call this function g of x. So the limit of g of x as x approaches infinity is going to equal what? Well, as x gets larger, my g of x values, my function values, go further into the negatives. So that would be equivalent to negative infinity. And then we can look at this other side. As x goes towards negative infinity, the limit of g of x also goes towards what? It also goes towards negative infinity. Now, here's an example of an odd function. And just to note, we could also have the reverse as it comes up this way, just to get an idea of the different shapes of graphs we could potentially be working with, those different types of functions. So now, in this case, as x goes towards a positive infinity, what happens to our function? Our function goes towards negative infinity. So here we'll have the limit as x approaches infinity of some function. Let's call this one h of x, just to mix it up a bit. That's going to equal a negative infinity. Whereas when we take the limit of h of x as x approaches a negative infinity, that means x is moving further to the left, then our function is continually increasing. So that function is going to head towards infinity. So those are different cases when we have a limit at infinity where the result is infinite. So now let's take a look at limits at infinity that are finite. So as we approach infinity or negative infinity along that x, for some functions, the limit is a finite real number. So the function will approach some finite number. For example, if we look at this first picture on the left, the limit of our function, let's call our function f of x, as x approaches infinity, is going to be equal to what? Well, as x gets larger, then our function goes closer and closer to what value? That's a negative 5. And also let's look at as x goes to the left. So the limit of f of x as x approaches negative infinity, so goes further into those negative numbers, that limit is also, well, where is our function going towards? it's headed towards a y value of -5. So the limit of f of x as x approaches negative infinity is also a -5. And here, if you remember from our previous worksheet, we also have this vertical asymptote at x equals 0. So if you can envision what makes that vertical asymptote, that's when we have a factor in our denominator that makes our function undefined that we can't cancel out. So because this vertical asymptote is at x equals 0, we know that we have an x in our denominator that we weren't able to cancel out. And let's move on to one more picture. I left the grid lines on each of these so it was easier to see. Let's look at the limit as x goes towards some positive infinity of our function. I'll call this one f of x again. If we look at this, as x goes towards positive infinity, what happens with our function? Well, if we follow along with our function, we're getting closer and closer to whatever this value is here, and that value is a +1. So the limit of f of x as x approaches infinity equals 1. Now let's take a look at the limit of f of x as x approaches negative infinity. And in this case again, we have the same result. As x goes towards negative infinity, you can see that the function is heading towards that same value of a +1. And just to keep us thinking, what's that vertical asymptote in this case? Our vertical asymptote occurs at x equals 0, because as x approaches 0, our function approaches positive infinity from the right, and our function approaches negative infinity from the left. So those were two quick pictures of limits at infinity, so as x goes towards a positive or negative infinity, where we get finite values as a result. But since we're on the topic of asymptotes, let's talk about the next type of asymptote that occurs, and that's going to be a horizontal asymptote. So if you can think about a vertical asymptote, now we're going to have a horizontal asymptote, which, if you look up above, occurs in both of these examples when we take the limits at infinity and get finite values. That's when we get these horizontal asymptotes. You can see that in our first picture, the function continued to approach what? It continued to approach the line y equals -5, or f of x equals -5. That function goes close, almost hugging that line. Whereas in the other example, same deal. Those limits at infinity, when they're that finite value, that's what our horizontal asymptote is equal to. So in this case, it's y equals 1. So when we work with vertical asymptotes, it was as x approached some finite value, we got an infinite value. So as x approached a, then we knew that that vertical asymptote was x equals a. But in the case of horizontal asymptotes, we're taking the limit as x approaches infinity, and if we get some finite value L, well, then our line, our horizontal asymptote, is y equals L, whatever we get as the result of that limit. So again, a horizontal asymptote occurs when the limit of our function f of x as x approaches either a positive or negative infinity is equal to some finite value L. So if the limit of f of x as x approaches positive infinity equals L, that's a horizontal asymptote. Or if the limit of f of x as x approaches negative infinity equals some other L, well, that is also a horizontal asymptote. And when I say horizontal asymptote, I'm talking about that line y equals L. That is our horizontal asymptote. Whatever the limit is, as x approaches infinity or negative infinity, if that limit of our function is finite, that's a horizontal asymptote. And I just want to make a note that as x approaches positive infinity and as x approaches negative infinity, they don't have to be that same exact value L. We could have the limit of f of x as x approaches some positive infinity equal, let's say, 3. Well, then we know we have a horizontal asymptote at y equals 3. And within that same function, we could have the limit as x approaches negative infinity of our same function, f of x, equals something like a -1. Well, then in this case, we have two horizontal asymptotes, y equals 3 and y equals -1. So again, both towards positive infinity and negative infinity do not have to be the same exact value, but if they are that same value, we only have one horizontal asymptote. So now that we've discussed this a bit, let's continue on to the next page. So quickly, I want to discuss limits at infinity for polynomial functions, or linear functions, because a linear function is a polynomial function to a first degree. But if you think about these polynomial functions, we're either going to have an even function or an odd function. So that's where we're going to go towards either an infinity or negative infinity as x approaches infinity or as x approaches negative infinity. It all depends on the degree of that polynomial as well as the sign of the coefficient with that highest degree. So let's jump into 1a, explaining this a little more in depth. So in 1a, I have the limit of negative 5x cubed plus 4x minus 9 as x approaches infinity. Now what I like to think about is what really dictates the growth of my function. Is this 9 really making a difference when I get towards the tails of my function? No. Is this 4x? Actually, no, it's not. It's whatever has the highest degree. So it's this negative 5x cubed that's dictating where my function is heading. So if I'm taking the limit of this as x approaches infinity, think about taking very large numbers that are, well, we're headed towards a positive infinity, so very large positive numbers, and continuing to increase that. Well, that's going to head towards infinity. X cubed is heading towards some positive infinity as x heads towards infinity. However, what is that multiplied by? That is multiplied by a negative 5. So because I have that negative 5 out in front, I have a negative coefficient. The limit of this is actually a negative infinity. And you'll be able to see how this will make a difference if I had the limit of this same function as x approached infinity, except I'm just going to leave off 4x and 9 for now because those aren't dictating the growth of my function. If I had this limit, and as opposed to going to a positive infinity, I now went towards a negative infinity. Well, let's think about this. If we're heading towards negative numbers for x and very large negative numbers, a negative number cubed is still what? It's still a negative. So we have a negative and the coefficient out in front is also a negative. A negative times a negative is going to give us a positive. And because we're cubing this, our values are continually getting larger. So we have a very extreme large negative number multiplied by another negative number. That's going to be a very large positive number. So in this case, when x heads towards negative infinity, we would get positive infinity. And going back to whether it's even or odd functions, you can see in this case that it's an odd function. So it makes sense that as x goes one way, we're heading towards a negative infinity, and when it goes the opposite way, we're heading towards a positive infinity. In example 2, x squared minus 3x is our function. We're taking the limit of that as x approaches a negative infinity. So again, what's dictating the growth of our polynomial? It's not this negative 3x. It's what has the highest degree, which in this case is x squared, or 1x squared, because 1 is that coefficient out in front. So our coefficient out in front is indeed positive, and we have x squared. Now, as we go towards a negative infinity, we're going towards some infinite number, but that negative number is getting squared. So as opposed to going towards negative infinity, we're going towards a positive infinity. So let's take a look at if we took the limit as x approached a positive infinity now. Well, if we still have x squared, I'm just going to write what's dictating my growth of my function in this case. As we go towards a positive infinity, a very large positive number squared is still a very large positive number. So this also goes towards infinity. And it does indeed make sense because this is an even function. So getting infinity as x goes towards positive infinity and as x goes towards negative infinity makes sense. Now before we jump into this next section on our worksheet, which deals with rational functions, I just want to continue thinking about polynomial functions, but let's think of a polynomial function where it's in the denominator. So some constant over a polynomial function. Like for example, if we had 1 over x squared. and think about taking the limit of that as x approached infinity. Well, we've done examples like this, so if you remember back to a previous worksheet when we talked about those vertical asymptotes, as x got closer to that finite value, our denominator was undefined. And with that, a lot of times we had some constant over a denominator that got smaller and smaller and smaller. So when we took the limit of that, the overall fraction got larger. Well, the reverse is true here. If our denominator is getting bigger and bigger and bigger, and we have some constant over that denominator that's getting infinitely large, then our overall fraction gets smaller. So if we have some constant over a polynomial, as x is going towards infinity, this is going to go towards 0. And if you want to think of it in terms of numbers, let's take a look like we did previously. Let's look at 1 over 1/10. Well, that was equal to 10. Let's look at 1 over, let's make 1/10 larger. Let's go to 1. 1 over 1 is equal to 1. So let's make this denominator even larger. Let's go 1 over 10. Well, that's 1/10, or 0.1. Or if we think about going even larger in our denominator, 1 over 100, well, that's going to be 0.01. Or if we got even larger, think about doing 1 over 10,000. That's 1, 2, 3, 4 zeros. So I'm going to have to shift my decimal place over 4 times. So I'm going to have 1, 2, 3, and then that 4th decimal place. That's 1/10,000th. So you can see I started with some number 10 and got smaller and smaller as my denominator got larger and larger. So remember this when we move on to the next examples dealing with rational functions. So polynomial functions are fairly easy to work with. Let's look at limits at infinity for rational functions. So that's when we're taking a polynomial and dividing it by another polynomial. As we take the limit of rational functions, we may approach infinite values, but we may also approach finite values. Where up above, when we were dealing just with polynomials, we were always going to approach an infinite value. Whereas with rational functions, our limit can be both infinite and finite. So let's take a look at a few of the examples below. So in part A, we're looking at the limit of 5x cubed plus 3x minus 1 all over 2x plus 7, and that's as x is going towards a positive infinity. So we know that this function goes towards positive infinity because it's a polynomial with a degree of 3 and the coefficient is positive. And we also know that this goes towards a positive infinity. But that doesn't necessarily mean our overall function goes towards positive infinity, because what makes one infinity larger than another infinity? That's hard to even conceptualize. So what we're going to do is we're going to divide everything by the highest degree in the denominator. So if we're looking at our denominator, what's our highest degree? Our highest degree is x to the first. So we're going to take the limit as x approaches infinity of, think about dividing everything by x. That's like multiplying the numerator by 1 over x and the denominator by 1 over x. If we multiply by 1 over x all over 1 over x, that's multiplying by 1, so we're not changing the value of this limit at all. We're just manipulating it so that we can solve it. So dividing everything by that x, like I stated, we're going to have 5x cubed all over x plus 3x all over x minus 1 over x, and that's our numerator. So in our denominator, we're going to have 2x over x plus 7 over x. Now we're ready to simplify this down and evaluate the limit. If we take the limit as x approaches infinity of our function now, let's see what happens. This x in the denominator will cancel out with one of the x's in the numerator to leave us with x squared. This x will completely cancel out. I can't do anything to this third term in the numerator. And my denominator, my x that's with 2 will cancel out, and I can't do anything to that second term. So rewriting this, I'll get 5x squared plus 3 minus 1 over x all over 2 plus 7 over x. Now, how exactly did that help us? Well, let's remember some of those basic limit laws. If I have a constant over x as x approaches infinity, what's the limit of this if I was to break this up from the 2? Well, the limit of this goes to 0. As x approaches infinity, 7 over x approaches 0. What happens to 1 over x? Well, as x approaches infinity, 1 over x, a constant over x, also approaches 0. So I have this 5x squared plus 3 minus 1 over x all over 2 plus 7 over x, where my 1 over x and my 7 over x are both going towards 0. If I'm just looking at what I have left, I have a constant in my denominator, and in this numerator, my numerator is going to continue to get larger because that has a degree of x squared. As x goes towards infinity, my numerator is continuing to get larger. So because 3 is a constant, 2 is a constant, and this is my only function with x, this gets arbitrarily large. This goes towards infinity, so overall, my limit approaches infinity. And that would be the same case even if x was approaching negative infinity, because I have this x squared here. Once I simplify down, negative infinity or some large negative number squared is going to continue to be a large number, but then it would be positive. This coefficient is positive, so again, that would also be a positive infinity. Now what I did is in part B, I have the same exact function, except now I have my numerator in my denominator and my denominator in my numerator. So now my highest degree that I'm going to divide everything by is, well, it's the highest degree in the denominator, so that's going to be my x cubed. Let's simplify down and see what happens. Well, my 2x over x cubed will become a 2 over x squared. My 7 over x cubed remains the same. And in my denominator, I'll have 5x cubed over x cubed goes to 5. 3x over x cubed goes to 3 over x squared. And then negative 1 over x cubed will remain the same. So think about taking the limit as x approaches infinity. Well, if I have a constant over some polynomial of x where that's continuing to go towards infinity, a constant over a denominator that continues to get larger, that overall fraction is going to get smaller. So 2 over x squared is going towards 0. As x approaches infinity, 7 over x cubed is also going towards 0 or approaching 0 as x approaches infinity. And so are the other two in my denominator. So if my numerator is approaching 0 and my denominator is just going to be some constant of 5, well, 0 over 5 is going to be 0. So this limit is equal to 0. So far I've taken the limit of a rational function and I've gotten an infinite value, and I've taken the limit of a rational function and have gotten 0. I can also take the limit of a rational function and get some other finite value. Let's take a look at c. If you think about c, what's our highest degree in our denominator? That's going to be x to the 4th. So get ready to divide everything by x to the 4th. And I'll go ahead and do this in my head so that I don't have to continue to write it out. So 6x to the 4th over x to the 4th is going to be 6, minus 20x cubed over x to the 4th is going to be 20 over x. And in my denominator, 8x to the 4th over x to the 4th is 8, minus, if I have 4x squared over x to the 4th, that's going to be 4 over x squared. Then I have 3x over x to the 4th, which is going to be 3 over x cubed. And then lastly, I'm going to have my 5 over x to the 4th. Again, what I did here is I divided everything by x to the 4th, which you can envision taking 1 over x to the 4th over 1 over x to the 4th and multiplying it through to everything. So essentially multiplying by 1, not changing the value of this limit, just manipulating it a bit so that we can work with it. Think about a constant over a number that continues to get larger, that overall fraction is going to get smaller. So 20 over x is approaching 0, 4 over x squared is approaching 0, 3 over x cubed is approaching 0, 5 over x to the fourth is approaching 0. If all of those things are getting closer to 0, and I have some constant of 6 over some constant of 8, this limit is going to be exactly that, 6 over 8. And 6/8 in this case simplifies down to 3/4. Now, doing all this work to evaluate these rational functions, dividing by that highest degree in the denominator, gets a little tedious. But as you can see, there's three main cases. When the numerator has a degree that's higher than the denominator, when the numerator has a degree that's smaller than the denominator, or when the degrees of the numerator and denominator are the same. So using this and thinking about how the functions grow, what dictates the growth of those polynomials, we're going to be able to do similar rational functions, but a lot quicker. So let's go over those different cases one more time. So one case is that, like in example A, the numerator degree is greater than the denominator degree. So I'm going to write here, the degree of the numerator is larger than the degree of the denominator. And when this is the case, if we take the limit of that function, think about it. Let's go back up to A. What's dictating the growth of either of our polynomials? It's those highest degree. So in the numerator, it's that 5x cubed, and then in the denominator, it's 2x. So if I covered the remaining terms of my polynomials up, you can see that 5x cubed is dictating my growth in my numerator, and 2x is dictating my growth in my denominator. Which one's growing faster? My numerator or my denominator? My numerator is, because it has a higher degree. So if my numerator is growing faster, that means that that is going towards some arbitrarily large number way faster than my denominator is, which means overall my function is going towards infinity, or potentially negative infinity, depending on the sign of those coefficients. However, when the degree of the numerator is larger than the degree of the denominator, we're going towards some infinite value for the limit. So I'm going to make a note that when the degree of the numerator is larger than the degree of the denominator, our limit is going towards some positive or negative infinity. Now, the other case was, like in example B, when the degree of the denominator was larger than the degree of the numerator, or the degree of the numerator is smaller than the degree of the denominator. So in the first case, the degree of the numerator was larger. In the second case, the degree of the numerator is smaller. So if you think about the degree of the numerator being smaller, that means our denominator is growing faster. So if we have something growing faster on our denominator, that means our overall denominator is getting larger, which means our overall fraction is getting smaller. Our denominator grows so much faster than that numerator, making the overall fraction go towards 0. So the limit, when the degree of the numerator is smaller, is going to be 0. And lastly, like in C, we have it where the degree of the numerator and the denominator are the same. So here I've wrote that the degree of the numerator is the same as the degree of the denominator. And when those degrees are the same, let's take a look what happened. When those degrees were the same, our solution was, well, it was the coefficient of that largest degree in the numerator over the coefficient of that largest degree in the denominator, 6 over 8. So when those degrees are the same, we take the coefficients. So that limit is going to be equivalent to, when the largest degree of the numerator matches that largest degree of the denominator, it's going to be the coefficient of the numerator's largest degree over the coefficient of the denominator's largest degree. So knowing this helpful hint, example 3 is going to be so much easier to do. Let's take a look. In part A, we're going to evaluate the limits as x goes towards infinity in each. What's the largest degree in our numerator? That's x squared. So we have a 6x squared. What's that largest degree in our denominator? That's an x squared as well, so 3x squared. Because the numerator degree matches the denominator degree, the degrees are the same, we're going to take the coefficient of that numerator's largest degree over the coefficient of the denominator's largest degree. So that's going to be 6 over 3, which equals a positive 2. Look how much easier that was than how we had to attack part C up above, all that division. Moving on to B now, the highest degree, what's dictating our growth in our numerator is that x to the 6th, and the highest degree, what's dictating our growth in our denominator is x to the 8th. The denominator has a larger degree, meaning that the numerator has a smaller degree than the denominator. The denominator is growing faster, so the overall limit is heading towards 0. And then lastly, you can probably guess because I tried to put an example of each. If we have a degree of x to the 4th in our numerator, that's a 7x to the 4th, and the largest degree in our denominator is x cubed, well, x to the 4th is growing faster than x cubed, and we're taking that limit as x goes towards a positive infinity, and I also have that positive coefficient, so this overall limit is going towards infinity. So now, tying this all back together with what we did up above, which of these functions has a horizontal asymptote? That's when we get a finite value for the limit of our function as x approaches infinity. So in this case, A would have a horizontal asymptote as well as B. C would not because that's approaching infinity. So our horizontal asymptote for A would be that y equals 2, and our horizontal asymptote for B would be that y equals 0. And up above, quickly, in part A, our limit went towards infinity, so A doesn't have a horizontal asymptote. B, our limit of our function as x approached infinity went towards 0, so y equals 0 is a horizontal asymptote. And for C, as x approached infinity, we got 3/4, which is a finite value, so y equals 3/4 is also a horizontal asymptote. Now, let's quickly just discuss limits at infinity for other functions other than polynomials and rationals, like trig functions, or e to the x, or even the ln of x. If we look at part A, the limit of the sine of x as x approaches infinity, could we use the squeeze theorem for this? Let's see. We know that the sine of x is always trapped between -1 and 1. So -1 is always less than or equal to the sine of x, which is always less than or equal to 1. If I took the limit of a constant as x approached infinity, that limit would be a -1. If I took the limit of 1 as x approached infinity, well, that's a constant, that's also going towards 1. So because those do not equal the same thing, I cannot use the squeeze theorem. And even if you think about what the sine of x looks like, it's going to continue to oscillate forever. It's always going to oscillate between -1 and 1. So it's not heading towards any finite value, it's not heading towards infinity, it's not heading towards negative infinity. We just say that the limit does not exist. Let's take a look at this other function, cosine of x over x squared. Let's try the squeeze theorem with this. Well, we know that the cosine of x is always between -1 and 1, just like the sine of x. But our function is the cosine of x over x squared, so I'm going to put everything over an x squared. But these inequalities will still hold true. So now I'm going to take the limit of -1 over x squared as x approaches infinity, and I'm going to take the limit of 1 over x squared as x approaches infinity. And let's go ahead and zoom in on this. If I'm taking the limit of -1 over x squared as x goes towards infinity, that denominator is getting larger and larger and larger. So regardless of the sign, I know that my overall fraction is going towards 0. So this limit is equal to 0, as well as this other limit. So because both of my limits are equivalent to 0 and cosine of x over x squared is trapped in between, I know that that limit is also equal to 0. So technically, even though this function is oscillating, it's heading towards 0, that still makes y equals 0 a horizontal asymptote, because our function is approaching that horizontal line, y equals 0. Now, let's quickly think about the ln of x, because the ln of x and e to the x will continue to come up for later lessons in this calculus series. So let's just quickly draw the ln of x out. And if you think y equals the ln of x is the inverse of that e to the x. So you really only need to know how to draw one of those and then just reflect it over the y equals x line. Drawing y equals ln of x, I know that the ln of 1 gets me to 0, and then it continues on. So here is y equals ln of x. And I'll go ahead and do it in a different color so that you can see it separated from those axes. So if this is y equals ln of x, as x goes towards infinity, what does my function go towards? My function is also going towards infinity. It continues towards infinity, so the limit of ln of x as x approaches infinity is also infinity. Think about the limit of ln of x as x approached a negative infinity. Well, we wouldn't be able to do that because negative infinity, or values to the left of 0, are not in our domain for x. So the only other limit we'd be able to do with ln of x, besides positive real numbers, would be taking the limit as x approached 0, but it would have to be 0 from the right. We would not be able to approach from the left because those values don't fall in our domain. So the limit of ln of x as x approaches 0 from the right, you can see we would go towards negative infinity. Now for part D, we're going to do e to the x. So let's quickly graph that just as a refresher. If here is x, here is y, e to the x is that inverse of the ln of x, so e to the x goes like so. So when we're at 0 in the x, we're at 1 in the y. Just as when we did the ln, when we were at 1 in the x, we were at 0 in the y, the reverse is true. So if this is y equals e to the x, as x approaches infinity, you can see that e to the x also approaches infinity. And the domain of e to the x is all real numbers. So if I were to take x and approach negative infinity, well, the limit of e to the x as x approaches negative infinity would be 0. But going towards positive infinity, it's a positive infinity. So if that limit of e to the x as x approaches negative infinity equals 0, well, we have a horizontal asymptote at y equals 0. Even though the other side goes towards infinity, we still have that horizontal asymptote of y equals 0. Now these next two, I think, tend to trip people up a lot, but just remember your basic algebra skills. A negative exponent can be written as a positive in the denominator. So I'm going to rewrite both of these before I even take the limit. So this is going to be the limit of 1 over e to the positive x as x approaches infinity, and this is going to be the limit of 1 over, again, e to the positive x, but as x approaches negative infinity. So let's think about taking the limit of 1 over e to the x as x goes towards infinity. Well, what happens to e to the x as x goes towards infinity? Remember, e to the x as x goes towards infinity also goes towards infinity. So a fraction where we have a constant over a number that's getting larger and larger and larger, that overall fraction gets smaller and smaller and smaller. So this goes towards 0. Whereas below, we have the same fraction, except now we're going towards negative infinity. So for the limit of 1 over e to the x as x goes towards negative infinity, what happens as e to the x? Remember that graph? E to the x as x goes towards negative infinity goes towards 0. So because e to the x is getting smaller and smaller in our denominator, our overall fraction is getting larger and larger. So the limit of 1 over e to the x as x approaches negative infinity is infinity. So that was just some practice of working with other functions that you will continue to use throughout these calculus lessons. I just think sometimes it's good to stop and talk about them and visualize them to pull everything together. Now, one thing I want to do a quick review on is going to be asymptotes, which I'll do in the next video. So far, we've been over vertical asymptotes and horizontal asymptotes, but there is another type called the slant asymptote that I'm going to introduce in the next video, and then we're going to do an overall review. So feel free to continue on to that, but until then, good luck with your online learning.